Welcome to the next video on logarithms. We'll briefly review what we've done so far. We've found out that powers indicate repeated multiplication. For example, 3 times itself 5 times can be written as 3 to the power of 5. When you multiply numbers that have got the same number base, you simply add the exponents to get the answer. So 7 squared times 7 cubed gives you 7 to the power of 2 plus 3. When you divide by numbers with the same number base, you subtract the exponents. So pi to the power of 9 divided by pi to the power of 4 gives you pi to the power of 9 minus 4. Adding exponents only works if you have the same number base. You can multiply together 2 to the power of 2 and 2 to the power of 5 to give 2 to the power of 7. But you can't multiply 2 squared by 3 squared to get a simple power of either 2 or 3. The same is true for subtracting exponents. You need to have the same number base when you divide one number by another. 2 to the power of 5 over 2 to the power of 2 gives you 2 to the power of 5 minus 2. But 2 to the 5th over 3 squared does not equal either 2 cubed or 3 cubed. Any number raised to the power of 0 is 1. 3 to the power of 0 is 1, pi to the 0 is 1, 0.7163 to the power of 0 is 1. But the rules don't apply if the number base is 0. So whilst 0 cubed is 0, 0 squared is 0, 0 to the power of 1 is 0, 0 to the power of 0 is a rather contentious question, which we're not going to look at. In the same way, 0 to the minus 1 means 1 divided by 0, which can be interpreted as being infinity, but not necessarily. At the end of the last video, we were left to the question, what does it look like? As in, what do these numbers look like? 2 to the power of 4, 2 to the power of 3, 2, 1 and 0. So the obvious thing to do is to put them on a graph. Over here we have our data table, and here is the graph. On the x-axis we're going to plot 2 to the power of 0, 1, 2 and 3, and on the y-axis we're going to plot the result. 2 to the power of 0 is 1, of course, 2 to the power of 1 is naturally just the number 2, 2 squared is 2 times 2, which is 4, and 2 cubed is 2 times 2 times 2, which is 8. Our first number, 2 to the power of 0, is 1. Here's 2 to the power of 0, and here's 1. 2 to the power of 1 is just the number 2. 2 squared equals 4, and 2 cubed is 8. And that gives us this very distinctive upward curving graph. But points on a line are quite gregarious. They like to be joined together. So let's join the dots together. At first sight, this seems to be quite an unremarkable thing to do. But when we look at it a second time, this is asking a very, very strange question. Previously, we defined our powers as being a whole number. So if we go over here, for example, 2 to the power of 0 was just a single number 2 divided by number 2. 2 to the power of 1 is just the number 2 by itself. 2 squared is 2 multiplied by 2. Now that we've joined the numbers together, I can legitimately ask a question such as, what's 2 to the power of a half? And we can get an answer that it's a number somewhere between 1 and 2. It's about 1.4 to 1.5-ish. And in terms of our original definition, this is now getting very strange indeed. What on earth do we mean by a fractional power? How can you have part multiplication by a whole number? And specifically what we're going to answer is, what is the meaning of 2 to the power of a half? Actually, the answer is very, very simple. All we've got to do is multiply this number by itself. When we do, we can apply our usual rule for powers, these are both numbers with a base of 2, so to get the answer we simply add the exponents together. And 2 to the power of 0.5 plus 0.5 clearly gives me 2 to the power of 1, or just 2. In other words, we've discovered the square root of 2. If you're unfamiliar with the idea of a square root, it's defined in a slightly backwards way. In most of life, we're used to the idea of having a number and another number, multiplying one number by another and getting an answer. With square roots, we're asking the question the other way round. We're given the answer, and then we're asking what number, when you multiply it by itself, gives you the answer. In this case, obviously the answer is going to be 3, because 3 times 3 equals 9. And we write that using a symbol. We would write out that the square root of 9 equals 3. And we know it's a square root because there's no extra number here. If there was a number in here, it wouldn't be a square root, it would be the third root or the fourth root, and we'll get onto what that means in a moment. First of all, we'll look again at the square root of 2. We'll simply rewrite this, just to emphasize the notation, that 2 to the power of 0.5 actually equals the square root of 2. Of course, this leaves us with a question. What do these other numbers mean? We've found a single number, 2 to the power of 0.5, but what about 2 to the power of 1 1/4? What about 2 to the power of 2 1/2, or 2 to the power of 2.75? What on earth do these other numbers mean? There is more than one interpretation. One way of understanding these fractional powers is to think of them in the following way. We'll take 2 to the power of 5/3. I can understand that as being two separate instructions. The first instruction is 2 to the power of 5. And then the second instruction is to take that number and find the cube root, which is a number that when you multiply it by itself 3 times gives you 2 to the power of 5. If this is true, I should be able to carry out this calculation as 2 to the power of 5/3 and get an answer, and then carry out the calculation 2 raised to the power of 5, then take the cube root and get the same answer. Here's the first calculation. 2 raised to the power of 5 divided by 3. And that equals 1.1748 approximately. We'll put that in the memory. Now I'll carry out the calculation the second way. 2 raised to the power of 5 gives me 32, and then I find the cube root. And this number ought to be identical to the number that's in the memory. So I'll hit the memory readout button, and nothing's changed. I'll repeat, this is not a mathematical proof, but it does demonstrate that this is one way of interpreting these fractional powers. I can make this as complicated as I want. I could have 2 to the power of 355 over 113. So that would be 2 to the power of 355, and then I would take the 113th square root of that, so a number which when multiplied by itself 113 times gives me 2 to the power of 355. We've gone a long way in the last video. We've gone from the idea of whole number multiplications to the idea of some sort of fractional part way between multiplying whole numbers together idea, and we've struggled to interpret it but found a way that kind of works. We can interpret these numbers as being, for example, the square root of 2, or we can interpret as being a number squared and then finding the third root of that. In the next video, we'll start using this idea of fractional powers to do some practical calculations using log tables. See you in the next video.